Hello everyone, I am Akshat Singh, a third year BTech student of Engineering Physics. Today I am going to show you a overview of Hall effect experiment. So, what is Hall effect? Let's take two magnets. A magnetic field would thus be created between them, and then we will place an electrical conductor between it, and using some electric cables we will connect it to a battery, and using another set of electric cables we will connect it to a voltmeter. Then when we closely analyze it, we would see the electrons coming from the battery will start getting deflected inside the conductor, and this deflection happening will create a potential difference, and this complete phenomenon caused by magnetic field is called the Hall effect. So in this animation we saw how the Hall effect is happening. This effect was discovered by Edwin Hall in 1879, and this is utilized in various applications today, such as in magnetic field sensing, proximity sensing, position sensing, etc. Required apparatus. Let's see the complete apparatus of the Hall effect experiment. This is the digital Hall effect setup. This is the digital Gauss meter. This is the constant current power supply, and this is the stand to hold the Gauss probes and Hall probes, and these are the N-type and P-type germanium samples. And finally, this is the electromagnet. Now let's start with the experiment. Our aim is to demonstrate the Hall effect and to measure the Hall voltage and the charge carrier concentration in a sample material. Here we have germanium p-type and n-type as our sample materials. This experiment we will be seeing the variation of magnetic field on changing the current in this constant current power supply. So I have placed the Gauss probe here between these electromagnets, and I will now turn on the constant current power supply and this digital Gauss meter. So now we will just increment the current by 0.5 ampere to see the change in magnetic field. So here we see that at around 0.5 ampere the magnetic field comes out to be 370 Gauss, and if I go to 1 ampere, so it comes out to be around 774 Gauss. That is almost the double of the magnetic field obtained earlier at 0.5 ampere. Similarly, now we can also look at suppose 1.5 ampere. So we see here that it comes out to be around 1178 Gauss. That is almost 3 times the value at 0.5 ampere. This means there is a linear relationship between the current applied and the generated magnetic field. So after calibrating the Gauss probe, we get these readings, and it comes out to be a linear graph between the magnetic field and the applied current. So in this experiment, we will be trying to check the Hall voltage across the germanium p-type sample. This is the germanium p-type sample, which has been used to hold between the four probes. These are the width-wise terminals, and this is the length terminals. The width terminals are to be connected to the voltmeter so as to measure the Hall voltage across it, and these are the lengthwise terminals. This green one, which will be used to measure the current across the semiconductor sample. So we will connect these to the respective devices. So now we will place the probes between the electromagnet, that is the germanium p-type sample, and the Gauss probe, and we will also make sure to leave a gap between them. Now we will see the variation of Hall voltage and Hall current at a constant magnetic field. Here we have set it to 253 Gauss, and then on varying the Hall current by 2 milliamperes, we will see the change in Hall voltage and will plot the graph so as to get the Hall coefficient. At 2.04 milliampere we get 2.5 millivolt, then on further increasing we get at 4.63 milliampere we get 5.4 millivolt, and at around 6.15 milliampere we get 8.5 millivolt, at 8.07 milliampere we are getting 11.1 millivolt, and finally at 11 milliampere we get 14.1 millivolt. So similarly we will place the n-type germanium sample in place of the p-type germanium sample, so that we can also calculate the readings of the variation of Hall voltage with the Hall current, with the changing Hall current. So similarly for that also we will plot the graphs of the Hall current and Hall voltage, and using the slope of that graph we can measure the Hall coefficient for the samples, for the p-type and n-type samples, and the and for p-type the Hall coefficient would come out to be positive, and for n-type it will come out to be negative, as we will see later in the video. So now after penning down the results of the Hall voltage and Hall current for both the p and n type germanium wafers, we get these. This means that for p type germanium sample the slope is positive, and for n type the slope is negative. Now let's see some calculations required in order to find the Hall coefficient and the current density. So for germanium p type and n type, the Hall coefficient and current density are found out to be these after applying the formulae. So the final results are that I versus P plot demonstrates a linear relationship for both p-type and n-type germanium wafers, and although the slope is positive for p-type and negative for n-type germanium wafer, this means that the Hall coefficient is determining the type of germanium wafer placed between the electromagnets. Now let's see some applications of Hall effect. First one is the magnetic field measurement. Like, it can be used to measure magnetic fields, as in the Hall sensors they can detect both the strength and polarity of magnetic fields, and speed detection, that is they can detect the rotation of gears, shafts or wheels by sensing the changes in the magnetic field as they pass through. So this capability is also utilized in speedometers, tachometers, etc. The next one is proximity sensing. The Hall effect sensors can detect the presence or absence of magnetic fields, making them suitable for proximity sensing applications like liquid level detection, door position sensing, and other object detections in automations and robotics. And the next one is brushless DC motors. That is, these sensors are commonly used in DC motors to detect the rotor position and control its operation efficiently. This allows a smoother and more reliable operation in applications related to robotics. Thank you.